So here we go with page 2. On page 2, you have two multiple choice kind of questions. The first one has to do with all the following phase changes that release energy. Now on the retest, I'll change these choices. So it'll say something about molecules speeding up or molecules slowing down or something like that. It'll be slightly different. But in this case, releasing energy means the molecules need to slow down. And when they slow down, they lose some of the energy that they had, and it comes out in the form of heat. It's why the backside of your refrigerator always feels hot. It's because there's a gas inside the coils in the refrigerator that is compressed on the backside, and that releases energy.
Mm-hmm.
On the front side, it evaporates, and that absorbs energy and makes it cold. Okay, so we want to know which one releases. So when the molecules get closer together, they release energy. So one of the answers is C, and the other answer is D, because when things freeze, they have to slow down from the liquid phase to the solid phase. So the molecules are starting to move slower.
Right.
Okay, so those are the two answers there. These two numbers are key in answering question number 8. So you look at those two numbers. They represent how much energy it takes to make 1 gram raise its temperature by 1 degree. So which one takes less energy to raise its temperature?
449
Yeah.
joules of.
Joules per gram degree C. So the 0.449 takes less energy for iron to get hot than it does for the scandium. So if you have the same amount of energy that you're putting into both of them, and it doesn't take as much energy for this to get hot,
Right.
then that's the one that's going to get the highest temperature,
Okay.
given the same amount of energy that this does. It's kind of like if you heat a piece of styrofoam, and at the same time you put well, suppose you have a cup of styrofoam with boiling water in it. You can pour boiling water in a styrofoam cup and hold it in your hand.
Mm-hmm.
But you wouldn't want to pour boiling water into a metal cup and hold it in your hand because it'd burn your hand. Okay? So the metal cup goes to a much higher temperature because it has a much lower heat capacity. It doesn't take very much energy to make it get hot.
Okay.
All right, so the actual answer here was iron. And now I'm going to draw a graph on number 10 to answer the question number 9. So here's the graph I wanted to refer to on number 10. It's our normal cooling curve graph where you have multiple phases. Okay, remember this temperature was 0, and this temperature up here, 100. All right, so now go back to number 9. If you're at negative 10, that means you're down here somewhere. Like right there. And if you're going to 125, that means you're going to be up here somewhere. Okay, so down here, got a button push. I need to change my pin. So from down here up to about there. All right, so you have to raise the temperature up to melting. Then you begin to melt the ice.
Right.
Then you keep raising its temperature until you get to 100. Then it takes time for it to boil away. Then you capture the steam and continue to raise its temperature. So how many total steps do we have? 1, 2.
2, 3, 4, 5.
So the answer to that question was 5 steps.
Right.
All right, now let's do some problems. So we're going to raise the temperature of 100 grams of water from 30 to 110. Now if you're at 30, you're about right here.
Okay.
110 be somewhere up in here. So 30 up to 110. All right, so how many steps will this be?
This be 3.
Yeah, 1, 2, 3, like that. All right, does this first step involve a temperature change?
Yes.
Yes, so we're going to need to use a temperature change equation. Does the second step involve a temperature change?
Yes.
Yes? No?
Yes.
Which? Well, so you start over here at 100, what's temperature over here?
Oh, it's 100.
It's 100, so it didn't change,
So
did it?
okay.
Okay, so since it didn't change, you're going to use this equation, Q equals M HV. All right, and the last there's a temperature change here, isn't there? From 100 up to the final temperature.
Mm-hmm.
So then you're going to use a Q equals M CP delta T again. All right, so what is the M in this problem?
The M in this problem is the 50. No, the 100. Sorry.
100 grams.
100. Oh.
Oops. Oh, you saw that in there. Okay, 100 grams. Is this a solid or liquid or gas between 0 and 100? It melts at 0.
Right.
It boils at 100. So in between, what phase of matter is it in? Before it boiled, but after it melted?
Liquid.
Liquid. That means that you need to use the liquid heat capacity, which is right here. So that would be 4.18. All right, and the change in temperature, this delta T, what was this temperature? We started at 30, right?
Right.
So 30, and we're going to 100. So how far is it from 30 to 100?
70.
Yeah, so that'd be a 70-degree change. All right, so our first step would be 100 times 4.18 times 70. So we'd have 29,260. Here we go, 29,260. And that's joules, because everything else canceled.
Okay.
So that's step one. All right, I'm going to leave the units off here for simplicity's sake because I'm running out of room. But the units will be grams times joules per gram. You'll end up with joules. Okay, so the grams hadn't changed, has it? What was that?
It was 100 grams.
And the heat of vaporization is the same heat of vaporization we used earlier. It is 2,260. So if I multiply 100 times 2,260, I get 2, 2, 6, 0, and then 2 more zeros. So 226,000 joules. And then the last one, again, I'm going to leave the units off because it's getting tight. What's the mass again? Didn't change.
Right. It's 100 grams.
Oh, I didn't leave the unit off. I thought I was going to, but I didn't. Okay. And we're going to multiply that by the heat capacity. Oh, and what phase of matter are we in when it's above 100? Solid, liquid, or gas up in this area?
We are in solid.
No, you melted at 0, right?
Right.
So where are we up above 100? Solid. So
Yeah.
let's think about phases of matter for a minute.
Okay.
So below 0, it's a solid.
Okay.
You told me that after it melts, it's a liquid.
So we are
Then
in-
after it boils, it is steam. All right. So I'd have 100 times, I gave you the specific heat capacity for steam on the front page, 2.06, wasn't it?
Right.
All right, so I'm going to leave the units off. And then the change in temperature, since we are at 100 here and we're ending at 110, see 110 is the final one?
Right.
So how far is it from 100 to 110?
80.
No, not from 100 to 110?
Oh, 100 and 110. Oh, 10. Sorry.
Yeah, it's 10. Oops. All right, so now if I multiply 100 times 2.06 times 10, man, I'm not sure why my pen is going crazy on me. So 100 times 2.06 times 10 is 2,060. So now our final answer will involve adding all three of these numbers together. So we take this number and this number and that one and add them together. So 29,260 plus 226,000 plus 2060, 257,320. And that would be your answer for that question.
Okay.
All right, now the next question kind of similar. Let's draw the graph again. Up, over, up, over, up. So what was that temperature right here again?
It was 30.
No, right here,
Oh,
just
0.
0. And this one
It's
is
100.
100 because you're at the boiling point. Okay, so you want to go from 25. 25, would that be, it'd be in this area,
Right.
right? And you're going to negative 10, which would be down here. So how many steps?
2. Oh, 3. Sorry.
3. All right. So there's a temperature change in the first step. You're going from here, see the x-axis, temperature's changing, isn't it?
Mm-hmm.
So you're going from 25 down to negative 10. So the first step would be 25 down to 0. So you'd have Q equals M CP delta T. How far is it from 25 to 0?
25.
Yep. What state of matter are we in? Remember, below 0 it was
It was liquid.
liquid up here.
Mm-hmm.
Is that what you mean? Okay, so that's right. So we're in liquid phase. That means that you've got to use a heat capacity for liquid phase, and that's 4.18. So put that in for CP. And then what was the mass?
Oh, the mass is 50.
Yep, 50 grams. All right, so 50 times 4.18 times 25, 5,225. All right, second step, Q equals mass times heat of what? Are we boiling or melting or condensing or freezing or what? As you're going from here to here, what do you call that?
We call it
Call it freezing?
freezing.
Right. If you're going left to right, it's melting.
Right.
Right to left's freezing.
Okay.
All right. So you'd have 50 grams of water. And HF is 334 joules per gram.
Mm-hmm.
So 50 times 334, doing it on the calculator, 16,700. In our last step, we have to go on down to this temperature, and this temperature is negative 10.
Right.
Okay, so I'd have Q equals mCp delta T. We know the M hasn't changed.
Mm-hmm.
What is it?
It's going to be 50 grams.
And the heat capacity it gave you on the front page is 2.06. I'm putting the units on this one since I have more room. And the change in temperature is going from this temperature, which was, what temperature is that flat line?
It's 0.
Right, it's going to go down to negative,
10.
so that's a difference of how many degrees? From,
10.
yeah, it's just 10 degrees. So now we have 50 times 2.06 times 10 is 1,030 joules. So I add that to the other two numbers. Oops, I think I made a mistake on my calculator. So I got 5,225 plus 16700 plus 1030 equals 22,955. That would be the answer to question number 11. Now, one caveat here, not all the tests had 25 degrees on them. This one did. I think
Okay.
the blank copy you have doesn't have that on there. So everybody's is a little different on that question.